So we've been learning about confidence intervals, and we learned how to do a z-confidence interval. But now what happens if you don't know your population standard deviation sigma? Because if you don't know the population mean, you probably don't know the population standard deviation. So what are we going to do? So we have what's called our standard error. Since our theoretical standard deviation of x bar is our sigma x bar equals sigma over square root of n, we can estimate the standard deviation of x bar by s over n, where s is our sample standard deviation. So we can use our sample standard deviation to estimate everything. And instead of then calling it the standard deviation of x bar, we'll call it the standard error. So standard error of x bar is s over the square root of n. And as soon as you switch to using the sample standard deviation instead of the population standard deviation, we have to switch and use the t distribution. So we'll use the t distribution instead of the normal distribution. So this is what it looks like then. So if you're going to use a t confidence interval, we use this when we don't know the population standard deviation. You'll have your confidence interval, and it'll be x bar plus or minus, and you'll have this t alpha over 2 n minus 1. So it looks long and complicated. Sometimes I just prefer to write a t star, especially on my homework and things, and times s over square root of n. So it's exactly the same. We do everything exactly the same. Interpretations, everything's exactly the same. But we're going to use a t table instead of the normal table. So when you see this t, alpha over 2, n minus 1, what this means for us, this is our critical point. Just like our z alpha over 2. Alpha over 2 is the area in the tail, and n minus 1 is the degrees of freedom. We talked about the t-table once before, but it was very quick. And so you haven't spent a lot of time working with it, but if you remember, it does have degrees of freedom that you have to know. So this interval, this confidence interval, will be exact if our population distribution is normal, and it will be approximately correct if the sample size is large, at least 30. So just like for the z. And in fact, really the t-confidence interval is so robust that it's going to be safe to use unless our data is obviously not normal. So as long as it's just kind of close to normal, it'll be okay. Okay, and when we say obviously not normal, okay, or obvious outliers. Outliers really throw off the t distribution if you have bad outliers. Now, because our t distribution gets closer and closer to the standard normal distribution as the sample size increases, you could technically use the z confidence interval for a large sample size instead of the t. And a lot of textbooks do it that way, but in practice, I've never seen anyone do that in a research study. Okay. In practice, we will always just use the t distribution if that's appropriate because it's more accurate, just a little bit more accurate. So before we do a confidence interval, let's practice using the t-table. So you should all have a t-table in the very back of your guided notes if you want to flip to it. So this is what it looks like. The t-table always gives you areas to the right, unlike the z-table. And over to the left, it has your degrees of freedom. Across the top, those are the areas to the left, and the actual t values are on the inside. So it's very much not like the z-table. So these are the probabilities, or the areas on the top, and on the inside are your actual t values. So we want to use this table, or the table, to find the critical points for each confidence interval. So if my sample size is 10, what would my degrees of freedom be? So degrees of freedom is equal to n minus 1. So my degrees of freedom coming down here are going to be 9, 4, 13, 33, and 49. Let's see, and then it gives me the confidence level for each one. And then we want to find the area in would be the area in the right tail. Okay, so if I want a 90% confidence interval, that means we want 0.9 in the middle. And so how much is going to be left over for each tail? So 1 minus 0.9 is 0.1, and divide by that by 2, so we'll have 0.05 in each tail. So the area in the right tail, which is what I can look up on my table, is going to be 0.05. So go to your table. We want 0.05, and we said 9 degrees of freedom. So 9 degrees of freedom and 0.05 gives you a t-value of 1.833. So 1.833. Okay, my next one wants a 95% confidence interval. So if I have 95% in the middle, I'll do 1 minus that and divide by 2. So I get 0.025 is the area in each tail. So we'll have 4 degrees of freedom and 0.025 in the right tail. So 4 degrees, 0.025, looks like we're at 2.776. And then 13 degrees of freedom. Oh, I didn't find my, oh, it's 95% again, so we still have 0.025. So 13 degrees of freedom. 13, 0.025. Looks like we're at 2.16. So notice those critical values changed a fair amount from going to 4 to 13 degrees of freedom. And let's see, we need an 80% confidence interval, so we'll do 0.8, which means you'd have to have 0.1 in each tail. So we'll do 0.1 in the tail, and 33 degrees of freedom. Now as I scroll down, you're not going to see 33 degrees of freedom. So the question is, which way do you round? Or you can use an actual calculator. Most of your calculators probably have a function that will do this for you. Okay, but it turns out you'll always round down on degrees of freedom. So let's make ourselves a note that we'll round down for degrees of freedom. It's just because it makes it a little bit bigger. It's just the conservative choice. So for 33, we'll round down to 30. So 0.1 area, 30 degrees of freedom. Looks like we're at 1.31. And finally, our last one is 98%. So that would be 0.01 in each tail. So I can do 1 minus 0.98 and divide by 2. And then we have 49 degrees of freedom. We will still round this down to 40 instead of just kind of going back up to 50. So 40 and 0.01. Looks like we're at 2.423. So that's just to practice how to find our critical points. The next thing I'm going to want you to know is, how could you actually tell if your data is normally distributed? Because we said that we can use the t-distribution if we have a large sample size or our data is normally distributed. So we have something called a normal quantile plot, and it creates a scatter plot of the quantiles of our data set and the quantiles of standard normal distribution. So remember, quantiles are like, well, quartiles are 25th percentile, 50th percentile, 75th percentile. And so they just do that for all the quantiles, like 10th, 12th, 15th, etc. And so if your points on this plot lie close to a straight line, then the data is approximately normally distributed. So this isn't a picture of our actual data, it's a picture comparing it to the normal distribution. So if you get something close to a straight line, you say it's approximately normal. So all of these on the left side, they're close enough to a straight line that I'd say it's fairly, my data is fairly normal. Even this bottom one, it's not exact, but it's still not that bad. I would still feel okay with that. Okay. But if you look over here at these ones, notice how this one is definitely not a straight line. Okay, this one definitely not a straight line. Okay, these are not straight lines, so this data is not going to be normal. And we want that because starting now, every thing we do, I'm going to say, here's a picture of the data set. Does it look like it was normal, or was it a large sample size? Should you be doing the t-distribution? So one of the most important things in statistics is not knowing how to compute these things by hand. That's what computers are for. But computers don't check your assumptions. You have to actually see, should I use this test or this test or this test, and you have to be able to interpret it. So those are the most important things I want you taking out of this class. So now it's time to practice. One measure of a company's financial health is its debt to equity ratio. One bank wants to make sure that its mean debt to equity ratio is less than 1.5. To estimate the mean debt to equity ratio of the current accounts, the bank randomly selects a sample of 15 of its accounts. So that tells me my sample size is 15. Find a 95% confidence interval from you. So we're looking for a 95% confidence interval. We'll interpret the confidence interval, and then we'll also want to know, is it plausible that the true mean is less than 1.5? So the first thing I do before I actually do any work is I look at my graphs, okay, and I want to say, does this seem normal? You can look at box plots to see if it's roughly symmetric, okay? You can look at the histogram. Now, this isn't exactly normal, but it's not really that far off. It's kind of close to the curve, and the normal quantile plot is actually the easiest way to tell, even better than histograms, and that looks like a fairly straight line. So I would say this one is normal enough. It's not exactly normal, but that's okay. It's normal enough. And then you'll see in your homework, well, maybe not in your homework so much, but in class, I start to put in these descriptive statistics. This is just using Megastat to run the data analysis on the data. So you can see the count, that would be n. You can see the mean, that would be x bar. Sample variance, that would be s squared. And sample standard deviation is s. Now because it says that sample standard deviation, I know I have to use a t confidence interval instead of a z, because we know the sample standard deviation. So we know sample standard deviation. So we'll use t. The first step is always find your critical point. Which we'll do by drawing a chart. So we want 95% confidence interval. So 0.95 in the middle. 1 minus that is 0.05 and divide by 2, so we have 0.025 in each tail. So I know I'll have 0.025 in the right tail, so I can look that up. And then my degrees of freedom is always equal to n minus 1. So our case is 15, so 15 minus 1 equals 14. So we'll go to our table and then erase all the stuff we already have. We want 0.025 and 14 degrees of freedom. Looks like we're at 2.145. So this t, and I'm just going to call it t star, equals 2.145. T star is just a lot easier to write. So then to find my actual confidence interval, we'll use our formula. X bar plus or minus our t star, s over the square root of n. So x bar is 1.3433 plus or minus our t value is 2.145, s is 0.1921, and over the square root of 15. So 1.3433 plus or minus 0.1064, and that gives me the interval 1.2369 to 1.4497. So all of the algebra and computations are almost exactly the same as the intervals. You just have to use a new table to look it up. And how do we interpret it? So interpretations will be the same. What we're going to say is we are 95% confident that, and we're always 95% confident that it's the population mean, or the mean for all of the accounts. Okay, so the population mean let's see, we're talking about debt to equity ratio. For all the accounts, or population means all the accounts, is between 1.2369 and 1.4497. So when I look at this, if we're 95% confident that mu is between 1.23 and 1.44, is it plausible that mu is less than 1.5? Yes, because that interval is less than 1.5. So yes, it's plausible that mu is less than 1.5. So they're doing good. So in our next problem, we're interested in the mean gas mileage for all the cars in a certain model. We found a sample of 50 mileages. So that's my sample size is 50. We had a mean of x bar equals 31.56 and s equals 0.7977. So first, do we need to check to see if the sample looks normally distributed? And the answer would be no, because n is greater than 30. So just like with our z confidence intervals, you check two things. You say, is our sample size at least 30, or is our data normally distributed? And as long as one of those things holds, you're good. So what I want you guys to do is take the next probably about 5 minutes and do this problem by yourself, include the interpretation, and then we'll see what you got. Now keep in mind, if you use your calculator to find t star, you're going to get a slightly different result than me, but that's okay. So let's go over our results now. So when you look at this one, your critical point, you should have 0.025 in each tail. Your degrees of freedom should be 49. Now to use your table, you'll round down to 40 degrees of freedom, and we get t equals 2.021. Now, just in case you're interested, if you tried it on your calculator, you would have gotten 2.009. So it's very close, and the end result is like the same to the 10th place. So you'll get very similar answers. It's just the calculator can give to you a little more precise because you don't have to worry about rounding down. Let's see, so once I have that, I plugged everything in. So my x bar, t star, standard deviation, sample size, and I get 31.3 to 31.7. So we're 95% confident. Now, when you're interpreting these for the test, make sure you have it's the average or mean, and for all, so it's the population average. The average gas mileage for all the new cars is between 31.3 and 31.7. So somewhere around just over 31 miles per gallon. You seem fairly confident about that. Now that we've done, then let's see what's next. So the last thing we talked about last time was how to find the sample size that you might want for a certain width of a confidence interval for the z distribution. So we can do the exact same thing for the t distribution. The margin of error, again, little m for margin of error, is always the part you're adding or subtracting. So the t critical point times s over square root of n. So you can rearrange this to solve for n. So n is going to be your critical point, which you find the exact same way, times s divided by the margin of error that you want. Okay, and square. Now just keep in mind, before you take a sample, you don't know the sample standard deviation s, or the degrees of freedom, since you don't know the sample size, which makes this kind of difficult, right? What we will do is we'll take a preliminary sample to find s and the degrees of freedom, and then calculate the sample size we need for a new sample and desired margin of error. So it's not going to be exact, but it's kind of our best estimate. Now sometimes when you do this, because you have to take a preliminary sample, you could just take a completely new sample, but usually to save money, people combine the old sample and the new sample. Let me show you what we mean here. A fast food company wants to estimate the mean waiting time for orders at the counter. A sample of 35 randomly chosen orders gives a sample mean of 1.7 and a sample standard deviation of 0.9. So we have n equals 35, x bar equals 1.7, and s equals 0.9. So first, before we get into estimating or figuring out what sample size we need, let's just practice finding a confidence interval. So let's find and interpret a 99% confidence interval for the population mean waiting time. So if you want a 99%, we'll need 0.99 in the middle. And 1 minus that is 0.01, and divide that by 2, so 0.005. 0.005. You also need degrees of freedom, which is n minus 1, so 35 minus 1 is 34. And I think we have to round down. I think it only goes up to 30. So let's go check. Here's my 30. We want 0.005. Looks like we're at 2.75. So my critical point, T star, is 2.75. So let's find our interval x bar plus or minus our critical point times s over the square root of n. So x bar is 1.7 plus or minus T star, which is 2.75, times s is 0.9, square root of n is 35, square root of 35. So put this in your calculator. 1.7 plus or minus 0.39 gives me 1.31 to 2.09. And to interpret it, we are 99% confident the population mean waiting time is between 1.31 and 2.09 minutes. Oh, and there's one thing I forgot to do on this problem. Did we actually check to see if it was okay to use the t-distribution? Coming back up to the problem, before you start calculating, you should always check to see if you can use the normal distribution. So my sample size is 35. So n equals 35, that's bigger than 30. So we can use the t-distribution. Because just like the z, it has to be either normal or at least a sample size of 30. So we found our confidence interval, but if you look here at this 39, or 0.39 right here, that's our margin of error. So our confidence interval is 0.78 minutes long. We're going from 1.3 to 2.09. And that doesn't sound like a really big difference until you're talking about waiting time at fast food, because that's almost a full minute. So they're not really sure, or they're not very precise yet about what the true population mean is. Is it closer to 1.3, which is pretty good, or is it closer to 2.1? That's pretty slow. So the company didn't like that margin of error. They want the length of the confidence interval to be less than 0.1. So how many more observations do they need to achieve this? So one of the first things we notice here is they said they want the length to be less than 0.1. Our formula is for width. So we better change, or not width, our formula is for the margin of error. So we better change this length to the margin of error. So if the length is less than 0.1, then your margin of error is less than 0.05. So we just divide it by 2. The margin of error is half of your length. So our formula to find a desired sample size is n equals t star times s over m squared. You can't forget the squared. So T star, now all of these numbers we're just using from up above. So we already found T star. We'll just use that one again of 2.75. S is our sample standard deviation, which up above we know is 0.9. And our desired margin of error is 0.05. And we'll square that, which gives me 2,450.25. No. Oops, I paused that. So just to recap again, we need at least 2,451, but we already have 35, so that really means only 2,416 more. This next one now is new, but it's not as hard as it sounds, and again, our textbook likes to give you lots of formulas. I say don't memorize the formulas, just draw a picture and think about it each time. So we did confidence intervals, but sometimes we don't actually need an upper and lower bound. Sometimes we only need it bounded on one side. So for example, let's say you kind of want to know like what the population mean is, but you don't really care if it's really low, you just want to make sure it's not too high or something. So you might only be interested in, say, an upper bound. And so if you were going to look at an upper bound for a 95% confidence interval, you draw a picture like this, okay? And normally we draw two tails because we want a top and bottom. But in this case, if you only want an upper bound, you only need to draw an upper line. And if you want 0.95 kind of in the middle, but we only draw an upper bound, how much is going to go over here in this tail? There's not two tails, so how much is going to go in the right side? We'd have 0.05 in the right side. Okay. So if you only want one side, you'll only draw your picture with one side, and instead of having two tails to divide your area in, you'll only have one tail. So that's why if you come over here, their confidence interval starts at negative infinity because there's no lower bound. X bar plus or minus, and well, not a plus or minus because it's just the top bound, so just plus. And then we'll do a t, and notice here it has an alpha. They didn't put alpha over 2. They just put alpha because you don't have to divide it by 2 because you only have one tail. And then it's s over square root of n. And you do the same thing for a lower bound. But again, I try not to memorize these or work too much on the formulas. I'll just think of it as a T star and draw my picture. So we have a brand group is considering a new bottle designed for a popular soft drink. They found a random sample of 60 consumer ratings. So n equals 60. Now because n equals 60, that's a big sample size. And it doesn't matter what our data looks like, we can go ahead and do the problem. Okay. Let's let mu denote the mean rating of the new bottle design that would be given by all the consumers, so all means population, in order to assess whether mu exceeds the minimum standard composite score of 25. The brand group will calculate a 95% confidence lower bound. Because they only want to make sure it's at least 25, they don't really care about what the upper bound is, they just want to make sure they know what the lower bound is. That's why they're doing just the lower bound here. And when we're done, of course, we'll interpret it. Okay, we also know that x, they also gave us x bar and s, and we'll just remind ourselves n equals 60. So first thing I always do is draw my picture. And I start to draw two things, and then I say, wait, I only need the lower bound. So I'm only going to draw on that lower one. And they want 95%, so this will be a 0.95, and in this tail we'll have 0.05. And also check your degrees of freedom. So we'll have 60 minus 1 equals 59. And to use my table, I have to round this down all the way to 40 is the next thing on the table. So we go to our table, 40 degrees of freedom, we want 0.05, so we'd be at 1.684. Now, the t-table gives you the positive area, so this is 1.684, which means the one I'm actually interested in is over here at negative 1.684. The t-distribution is symmetric, just like the z-distribution. So even though it'll give you the positive one, the one you're interested in is just that negative one. So t star equals negative 1.684. And normally we would do a plus or minus, but we don't actually need to find the top value. So our bottom point will be x bar minus t star s over square root of n. And our top bound will be just infinity, because we're not really looking for the top. Okay, let's see. So we'll do x bar is 30.35 minus. Okay, so when you come back over here, they want a minus. We already kind of included the negative. You don't want to uninclude the negative, make it be a positive. Okay, so whether you have a positive or negative here, just make sure if you're looking for a lower bound that you keep a negative here. So 1.684. S is 3.1073 and square root of 60. And infinity is my top bound. So we're going to get 29.67 to infinity. So we are 95% confident that the population mean is at least 29.67, which they'd be happy about because that means it exceeded the 25 that they need to go ahead with this bottle design. And our next example is, what if we have a data set for one person and the hours they spend per week on homework? So here's our actual data sets. Let's see, how big is our sample size? If you count this up, last time I counted, I got 24. Now 24 is less than 30. So we'll have to check if the data is normal before we can do anything. Now we don't actually ever know the population data, or we wouldn't actually be doing this. So we always kind of check our sample data to see if our data looks normal. So first of all, when I look at this histogram, that histogram is far from normal, right? If you look at your box plot, you have all these outliers. And my normal quantile plot is definitely a curve and not a straight line. So this data is definitely not normal. And because we had a small sample size and it's definitely not normal, then we can't use a t or z confidence interval. Whichever one they might have asked us to use, we can't use either one. So because it's a small sample size and it's not normal, you can't use either one. You have to have either a big sample or normal data. If you come across cases like this, if your sample size is small and the sample population doesn't look normal, okay, we can't use anything from your confidence intervals or z or t confidence intervals. Or when we learn about hypothesis tests and other things like that, you can't use anything basically if your data is not normal or a large sample size. In this case, we'd use what's called a non-parametric method, but we don't learn about that in this class. Okay. But they have other kinds of confidence intervals that you could use instead.